Hello everyone. Today we are going to start a whole new branch of physics called electricity and magnetism. We are finally leaving the world of Isaac Newton behind. Now granted, his concepts are still going to come back into play because they're laws of the universe. However, we are going to start exploring a whole new branch of physics called electricity and magnetism. So we're going to start with electricity, and that sounds like it's a pretty big topic. When you think of electricity, you can't get away from it in your life. You use it all the time. So we're going to start with the basics of electricity. So let's get started. All right, so where does electricity start? Electricity starts with the topic of electrostatics. When you hear the word statics in physics, you should think of at rest. You can think of static friction, the friction when the object is at rest. And when you hear electrostatics, you may think of static electricity, which is fine. We'll cover that. So electrostatics is electricity at rest, which is a weird idea. We will start with the basis of all electricity, which is electric charges. And we're going to start with the smallest electric charges. For us, that is our proton and electron. All right. Now, this should be a review from chemistry, but we're still going to go over it just so we're all on the same page. So when you think of protons and electrons, you obviously think of the atom, which I drew here. You should recognize this as a helium atom because it has 2 protons, 2 neutrons, and 2 electrons. Okay. So notice that our protons are in the nucleus and our electrons are orbiting outside. Now I know you chemistry geeks out there are going to rip me because this is the old model of the atom. I'm well aware of that. I'm well aware that the electrons are more like an electron cloud. There's only probability in this space, and when I say that's chemistry, it's really physics because we're the ones that decide everything in science. So I'm well aware of all that. However, for this lesson and going forward, it's a lot easier to visualize our electrons orbiting around the nucleus, just like planets orbiting around the sun. All right. I know that's not literally the case, but for visualization purposes, that's the easiest way to do this. Okay. Okay, so working with our basis of electricity, which is our electric charges, there are 2 fundamental rules, all right? These are the basis of all electricity on how electric charges behave, all right? And you've heard this before. It's the idea that like charges repel each other and opposite charges attract each other. So if we take our protons and electrons, all right, if you have opposite charges, a proton and an electron, all right, they will attract each other. And if you have like charge, like a proton and an electron, they will repel each other. So attract and repel, we're going to say a lot, but just think of other words for that, which is push and pull, all right? These 2 are pulling each other together. These 2 are pushing each other apart. And we know from Newton that push or pull in physics is force. So essentially, these electric charges exert forces on each other, all right? And their directions are either repel or attract. They either go to each other or away from each other, all right? Now that force, and that this whole idea is called Coulombs Law. Coulombs Law deals with that whole idea, and Coulombs Law is an equation that deals with this idea of like charges repelling each other and opposite charges attracting each other. I'm going to do a separate video that gets into the math and how we use Coulombs Law equations so we can do problems. But for this video and this lesson, we're going over the general concepts of electricity. All right? Okay, now that we are aware of Coulombs Law and this idea of electric charges repelling or attracting each other, let's go back and look at the atom, all right? So if we look at the atom now, we have a very big problem with the nucleus, all right? So this cluster in here where the protons and the neutrons are located is called nucleus. Notice that the neutrons, they don't have any charge, all right? If a neutron walks on the bar and asks a bartender how much for a beer, what's a bartender going to do? Oh, he's going to look at him and say, for you, no charge. So the neutron doesn't have much part in this conversation about electricity and electrostatics. What we're focusing on here is the protons, all right? According to Coulombs Law, according to our fundamental rule for how charges behave, these protons should not want to be next to each other. They should be repelling each other and pushing each other apart, all right? Well, we know from Newton's laws of force that if these things are pushing each other away, there must be some force that is keeping them together. That has to be stronger than that repelling force, all right? And that force that keeps them together is called the strong nuclear force. The strong nuclear force, this electric force, Newton's law of gravity, they are 3 of the 4 fundamental forces in the universe, all right? So there's 4 fundamental forces in the universe, and what that means is every single force that you've ever heard of or ever worked with can be explained by one of the 4. All right, so we've been dealing with friction, we've been dealing with normal force, tension force. They are not fundamental forces. Those things can be explained by one of the 4. All right, so within this nucleus here, we have the strong nuclear force acting on the protons, and that dominates that electric force that wants to push them apart. All right, so with the strong nuclear force, that only is really effective inside the nucleus. We don't really deal with that on our day-to-day basis. So with that in mind, and having the idea that the strong nuclear force is going to act on these protons, that is going to keep the protons in the nucleus. So with these electrons that are outside, all right, our whole entire discussion with electricity going forward is going to be about what the electrons do. Because the protons are stuck. The protons never move, all right? They're stuck at home. They have to stay there. Whereas the electrons, they're not in the nucleus. They're not being affected by that strong nuclear force per se. So they can kind of do what they want sometimes, all right? And that's going to be a very key factor in our discussion going forward on how things get charges, how electricity is flowing. It's always about the negative charges. It's never about the protons. Yes, they still exert forces, but they cannot move, all right? And that is key. Okay, so now that we got the atom situated, we know about the strong nuclear force, let's revisit the electric force, which is Coulombs Law, all right? Coulombs Law is pretty interesting. It's very similar to Newton's law of gravity, or the gravitational force, all right? When I take this marker here, I know that the Earth is pulling this thing down, all right? I'm holding it up, so that's preventing it from moving, but if I stop this, then the Earth pulls it down. It's a pretty incredible idea in that the Earth can magically reach up and pull something down without touching it, all right? If we go back to the story of Newton with the apple, right? It's a pretty incredible leap that he could come up with the idea that the Earth could pull that apple down off the tree without even touching it. I can't do that. If I wanted to pull an apple off of a tree, I'd have to go over and physically touch the apple and exert a force on it, all right? Luke Skywalker can do that. Darth Vader can do those incredible forces, but in the real world, human beings can't. But the Earth can. The gravitational force is what we call a non-contact force. All right? It sounds like science fiction, but it's not. So if we go here to Coulombs Law, it's the same idea. This proton and this electron can pull each other together without touching anything. This proton pushes this proton away without touching each other. Same thing with electron. So that's a pretty crazy idea, and it's very similar to gravity. Now, just like gravity, the idea of how does that thing exert a force on something without touching it, how does that actually happen? Well, that's something that Newton never figured out, all right? It's a different topic for later. But if we go here, all right, we still have the same question. How in the world do these objects exert forces on each other without even touching? All right. I can't really do that. All right. But these things can. How does that work? Well, it took a while for people to figure this out. This is when people were figuring out electricity and magnetism. It was pretty much like the mid 1800s, or when technology kind of caught up to enable scientists to construct laboratories to examine these things. A guy by the name of Michael Faraday in London was the man. All right, he's the physicist who could pretty much figure out everything. All right, he is my personal favorite physicist in that his story is kind of interesting. It's different from a lot of the traditional physicists. He was a guy in England who came from the working class. All right, and back then it was the working people and it was upper class, and you didn't go between your two classes. All right, there was no opportunity there. So Michael Faraday was self-taught himself from books that he had to make, because he was a bookbinder's apprentice. So he worked his way into a science lab and taught himself everything. He didn't have a formal education like all the rich people had. So he was able to teach himself all these things, and he figured out that he had a knack for examining labs that were being, or experiments that were being conducted, and he could see in a different way than anybody else could see it. And he is the main physicist who's driving a main theories that turned out to be correct during E&M. It's incredible what he's able to do. All right, if you want to go research a physicist, he's the one to he's one of the main ones to go check out. All right, incredible guy, my personal favorite physicist. Now, one of the ideas, or one of the problems that Michael Faraday had to conquer was the idea of how do these things exert forces without touching. All right. And what he came up with is the idea of the electric field. All right. What he visualized was there are invisible lines of force being sent out from every electric charge. All right. So if I had a proton here, all right, emanating out of this thing in all directions, going through empty space, is the electric field. And I've drawn these with these lines. Now, it seems like it's just a weird idea. Turns out, though, the electric field is an actual thing. All right, it's really important. It's not just an idea that solves a little problem. These are actual, they're not quite objects, but they are things. It's a difficult way to describe these things. All right, so his idea was that surrounding all charges was an electric field. And what would happen is, if there was another charge placed in that electric field, then that charge would feel a force from the electric field. Okay, so if we have an electron placed right here, all right, well, we know that the electron is going to be attracted to the proton, okay? But it's not the proton that acts directly on the electron. All right, does it? What acts directly on the electron is this electric field in that spot. This electric field exerts a force on the proton that will make the proton go this way. All right, so it's the electric field that exerts the force on the charge. This thing actually doesn't directly exert the force on this thing. All right, now, we can look at it two ways. We can still use Coulombs Law because it does tell us the magnitude of the force and it still works, all right? But all the electric field does is gives us the reason on why Coulombs Law works, okay? Now, likewise, so this thing feels a force, all right? But the reason why it feels a force is because of the electric field. But why is the electric field there to begin with? Because of this. So we know if this wasn't here at all, the electric field wouldn't be there, and therefore this electron wouldn't feel a force. So this thing exerts it directly on there. That's why it feels a force, but this thing is sending out these things, so it indirectly exerts a force on this. An analogy would be if you're out and you see a really good, very attractive guy or girl, and you're attracted, they're attracted. You don't physically go over and grab that person and pull them to you and attract them to you. That's terrible. That we're not cavemen. That's like assault. All right. So how do you attract that other person? Well, you present yourself in a good way. You send out your mojo, if you will. All right. And they can feel that charm, that mojo, and they're attracted to you, from across the room. All right, because you're good looking, you're funny, you're smiling, you have good manners. They can feel that mojo, and that mojo attracts them to you. All right, so it's the same thing. It's like this proton is sending out this electric field, is sending out this mojo, and it's that mojo that attracts the electron, and vice versa. If you put a proton here, well, it turns out that this electric field will push away this proton. All right, this electric field will push this proton away. So with any electric field, the direction of electric field lines matter. All right, you can see in this one, protons, if they're in an electric field, will go with the lines of the electric field, and a negative charge, an electron, will go against the electric field direction. Okay, now if we look at an electron or negative electric charge, it also sends out an electric field. But the electric field for an electron has a different direction than an electric field from a positive charge. The direction electron here, direction electric field here goes into a negative charge. Whereas this one, you can see for a positive charge that makes an electric field, the electric field lines go away from a positive charge. And electric field made from a negative charge always points towards the negative charge. All right. So in this case, if I have a proton here, remember, positive charges when placed in an electric field, always go with the direction. So this thing would go with the direction of electric field. All right. And we can see that the proton is attracted and is going towards the electron. All right. And vice versa. If I put another electron here, all right, negative charges when placed in a separate electric field always go against the electric field lines. Okay, so since the electric field line is pointing this way, all right, pointing that way, the electron will go against that thing. All right. Now you got to be clear on the electric charge making the electric field and an electric charge placed in somebody else's electric field. So in this case here, we say this negative charge here, which we call big Q for our when we get into our equations, which is a different video. This electron is making this field. All right. So anything that makes the electric field for a negative charge, it goes into it. These charges are being placed in somebody else's electric field. All right. I send out the mojo. I don't feel my own mojo. Other people feel my mojo. That's kind of the idea here. All right. So if we look at electric fields, these lines represent electric field. I don't know what's making. I don't care. I don't know if it's a positive charge or a negative charge. All I know is in this space, there is an electric field, and you can see the directions of them. So that means if I put a proton in there, if I put this proton in this electric field, it will go with the direction of the electric field lines. If I put an electron, which is a negative charge, in the electric field, it always goes opposite the electric field lines. All right, so we don't always have to know what the other charges are to be able to figure out which way an electric charge will move, which is kind of important because eventually we're going to start, once we get out of electrostatics, these electric charges are going to be moving, and now we kind of know why. We don't always have to know what the other charge is at the end. All we got to know is what's causing them to move in that space. Okay? So I think that's the basics of electrostatics. That's where all electricity starts. Hopefully some of it was a review. All right, we're going to, there's going to be another video where I show you a demonstration of this stuff. Super exciting. All right, but we're going to see how an object can get an electric charge. All right, and when does it not have an electric charge, and what does even all of that mean? All right, so yeah, miss everybody. Hope you enjoyed the video. I know it's super exciting, and I'll see y'all when I see you. Bye.